we specifically left off at the objective tree for creating a new cup and specifically for kids. And then we started talking about how the Stanley was created and why it would fit easily marketable, why it would fit cost efficient, yada yada yada. Now, at the end of the last question, I asked the question, how did they know that the Stanley was the idea? Because as a company, they probably had multiple different engineers. Multiple different engineers probably had multiple different ideas. Even one person can have multiple ideas that they think might or might not work. So how do they come to the conclusion of which one is the best option? So what they do is that they use something called metrics. And it is a whole bunch of data, right? Data collected in a numerical form. That is consistent and unambiguous. What am I reading? Wait, please. Okay? And what do I mean by this? It means that if I came and you came and random Joe off the streets came, we would all get the same answer. And that's why we also call it numerical, right? We are classifying it in terms of numbers so that it's more consistent. So for example, we take a look at our objective tree over here, okay? Specifically, for example, these last little bits, right? And we can see, can we classify these last little objectives in a numerical way? For example, small parts. Yes, we can. We can say number of small parts, okay? But over here we have to specify. So for example, smaller than, or I think a general rule of thumb that parents use is can fit through a toilet paper roll. Toilet paper roll. Okay? And that over here will provide us with a numerical value because everybody will be able to count the same amount of things. All right, I'm going to skip over this creative design part because that is another part of metrics because it cannot be measured numerically. So we're going to skip over that one. Okay, we did small parts. We are going to now do easy to hold. Okay, easy to hold. For this one, for example, we can put the classification as, let me scroll now. Awesome. Okay. The classification for this one, to test it, we could say number of places where you can put your fingers. Again, we'll get a number. For cost, get a number. For what else? We have durability and we have heat resistance. Okay, we can say maximum heat test. So where it is put under pressure, where it's put under heat to see if it will last, how good it would last, and that will then factor into our cost, especially for transportation. Because remember, there are some products and some designs that cannot be transported all year long. So this one will also give us a numerical value, probably in degrees or Fahrenheit. And then we would do the same thing for minimum. Or maybe we should say maximum cold. And we'd get another number in degrees or Fahrenheit. Okay, now what do we do about this one? Creative design. What do we do about durable? What do we do about easy to drink from. These are all subjective, right? I might personally like to drink from a straw, somebody else might not like to drink from a straw. So these are all subjective to your own personal desire. So, how do we measure things that are more subjective, not numerical? There is no testing for us to be able to determine these things. Well, first things first, we need to make sure that there actually is no testing. We need to make sure that we have expended every single path to make sure that if there was any way we could collect numerical data, we could use it. So, for example, durability. How would you test durability? And the basic thing that people do a lot of times is that they break it down into multiple different segments. Okay, so durability. If I was just measuring durability, I'm gonna change my color here. Durability. Okay, I can create new metrics for just durability. So, for example, drop test. How many times before something broke? Okay, we get a number. We could also do, for example, for the Stanley, what could we do? Durability test. We could try shipment, right? Shipment. How well did it hold in shipment? And then we can create a scale. So, for example, we can say 1, it didn't change. And then we count up for how many things changed. Parts, pieces, elements, anything, number. All right, now let's take something else. Let's take a look at something else that we could use. Spill proof. Right? All right, we need to make sure that there's no way to test this. Is there a way to test this? And that's something question we have to keep asking ourselves. Is there a way to test any of these metrics, even if it's not necessarily traditional or ideal? For a spill proof, we could see, for example, we can count, we're going to get a number out of this. Liters, for example, spilled when turned upside down. Okay. And then let's take a look. What else do we have? Creative application of design. Okay. When you have a very subjective metric that you're trying to find some kind of numerical value for, worst case scenario, if you cannot think of anything, I will show you guys how we could find the unique creativity of a design. But when you guys can't find something, rule of thumb, collect data through surveys, right? Maybe do a trial consumer study, trial sale. And you can find your information through that. Now, specifically for unique design, you could do it one of two ways. You can either computerize it, or you can you could actually go in and do it yourself. And you would set different metrics for one specific aspect. So if it's unique or not, we could say how similar is the straw. Okay. And then over here, you'd put 1 through 5, comment. It's not using. Okay. It goes from not common to common. Okay. And then you could say, you could do this for every single component in your design. Now, this is subjective, is it not? Yeah, this is very subjective. Common, not common. That's why I suggest computerizing it. But what do we do with a metric that's still subjective? We create what we call a morph table. Okay? Sorry. A decision matrix. That's what we're doing. Morph tables in a little bit, I promise. Okay, well, let's do a decision matrix though. We first put everything over here, all of our questions over here. So for example, how similar is it to the straw? Similarity of the straw. Okay, and then we rate it 1 through 5. Okay, we have idea 1, idea 2, idea 3. Okay, this is when we're still viewing all of our possible ideas. Okay, similarity of the straw, similarity of the shape. And I don't like that. Okay, and then we would go through and we would give it a number, right? 1 is it's more unique, and 2 and 5 it's more common. So let's say I go, I give this one a 1, 3, 4, 5, 2, 1, and I just made these up. Okay, because this is just an example to show you guys how this would work. And then we take this, right? We take this and we add these up. So this one is 4, 9, and 3. The one with the least number is the most unique. So then we would choose idea number 3, right? And this is how we compare all of them. And then when you go for a unique design, then we can actually even give them a numerical value. We could say that, okay, the numerical value associated with this is now a 3, for example. All right? You just have to make sure that your scales match up so that you can actually use it adequately and properly and you don't get messed up. Okay. We're going to delete all of that. No. Okay. Actually, why don't we just scroll down? All right, now we get into morph charts. What if we have all of these ideas? We have all of these ideas. We have all this metrics. We have everything, right? Now we have an idea, but what if we don't have any idea? We don't know what kind of combination we could do. We have so many possible choices and so many possible decisions that we actually can't make a decision, right? We can actually put over here, we can put all the possible ideas. So I'm going to go idea 1, idea 2, idea 3, idea 4. All right, and for this one, I'm actually going to use the example of cars because I think it's easier to visualize, right? Could go ahead and create this into a nice table. Okay. And then on this side, we have characteristics. Right? So we could say headlights. We could have oval, rectangular, rounded, rectangular, and almond, for example. Okay? And then we would go through and we would say, for example, and sometimes I just want to note, sometimes we'll only have 2, I guess, options, but that's okay. Go through and just add every single option you can think of for every single characteristic. Okay, headlights, we can have trunk space. Right, we can have large, medium, small. And then we can go ahead and we can add another characteristic. For example, shape. Right, we can have over here boxy, and then we can have over here rounded. Right. For example, this would be the difference between, for example, say a race car that's more aerodynamic, and then a car like I'm pretty sure it's called the G wagon that's a little bit more boxy. And then we can go through, and this is very, very basic, but just bear with me here. We can go through and we can decide either through metrics, through preference, through material cost, through pretty much any constraint or any objective that we had on our objective tree, which option would be best suited for each one. So in terms of headlights, maybe rounded rectangular costs the least. Okay? Out of the trunk space, maybe the medium fits best with what we need. Right? Out of these two shapes, in terms of safety, maybe the boxy is more safe. We use our metrics, we use our objectives to get to these conclusions. And then now, instead of having 3 or 4 or 10 different options, right? Because you can mix and match these in so many different ways. Now we have a car. We know it has rounded rectangular headlights. We know it has medium-sized trunk. We know it has a boxy look. Okay? And that's it. That's how you do morph charts, matrix decisions. That's how you do metrics. And next time, we're going to be tying it all back. We now know all of this. We know how we got to a conclusion. We know how we made a decision. We know how we made the right decision. Okay? Now, what is a problem statement?